All right, so if you remember on Monday we talked about interest and we talked about growth and decay problems. I think we mentioned this formula right here, the final amount of, I think it was money, but this is anything actually. It doesn't have to be money, but it could be something that is compounding over a period of time. Compound interest, but interest normally has a financial aspect to it. So any subject, any material that is compounding, it's growing, it's reproducing, depending on its size. So, you know, it's there's 100 items, it's growing at 10%, and after that compounding period, there's going to be 110. If there was 200 items, then if it's still growing at that 10%, then after that compounding period of time, it's going to be 220. Okay, so the idea is that it's compounding based on a percentage. And we saw that was 1 plus, the one formula, 1 plus r to the t, I think. If it was, you know, this is just compounding a certain number of periods. Like, for instance, if money was compounded annually at this percentage rate, but then we expanded that to say if it was compounded multiple times throughout a year or whatever, end times, then what you do is you figure out, well, what's the percentage rate that would have been over a whole year? Like instead of 10% over the year, you cut it in half, 5% and 5%. So you divide that by the number of times you're compounding it. And then the exponent becomes n times t, where t might be like the number of years or the number of overall compounding periods, times the number of times you're compounding it per those periods. And you've got 1 plus if we're adding, if it's growing, 1 minus if it's decaying, if it's going away. And when we did the graph here, we kind of didn't do the graph, we looked at the table of data. If you start with $100 and then you're getting, or $1,000 or whatever, I think it's $1,000. That money starts to grow. We found out that it grows exponentially if you compound it annually. But then if you compound it semi-annually, it was even better for you, right? Y'all remember that discussion? It rose, it was still exponential, but it rose even faster. There was actually an increase. I don't know if I'd want to say shifting to the right. It's more of a shifting vertically. You start at the same amount, but for instance, this particular point, instead of having $110, now you've got $111 or something like that. So this was 1 time per year. This was 2 times that you compounded per year. And then if you compounded it quarterly, it was even better for you. So that's twice as much as this amount. But the thing is that it doesn't actually increase as much as it did the first time. So if you have your money compounded quarterly, it's better than annually, it's better than semi-annually, but it's not as good compared to the semi-annually as the semi-annually was better than the annually, if that makes sense. It's sort of like, well, you aren't in economics yet, but it's the law of diminishing returns. It's sort of like, it's kind of like, we'll say it's like in relationships. It's pretty cool sometimes. You see, if it's in some relationships, you see them the first time, you get to, oh, it's awesome, it's great, oh, it's good. Then you see them again, it's kind of like, yeah, okay, it's not so special. You see them again, you're kind of like, okay, yeah, it's pretty normal, right? Okay, so it's sort of like, you know, yeah, it's a little bit better every time, but yeah, not so much as it was those first couple of times. Okay, it's a terrible analogy, but you get the idea. Hopefully, you haven't ended up having friendships or relationships that are better every time. All right, but sometimes you get into these diminishing returns relationships. That's what you've got with this. In fact, if you compound it monthly, yeah, it's better, but not so much as that. And you could even compound it daily, minute by minute. All right. Now, obviously, the percentage rate is going to get smaller and smaller each one of those times because you're compounding it more frequently. What we find out is that this actually approaches a very particular graph. Later on this year, we'll talk about limits. And this, there's a limit that we're approaching, a specific value this graph right here. In fact, we could extend it out this way. We extend all of them out that way if you want. But the one that it's approaching is this graph right here. A equals PE to the RT. And that is what you would get if you were to continuously compound something. So like, not just every second, not just every nanosecond or every microsecond have it grow, but like every, infinitesimally small time frame, you were going to grow it by some sort of percent, okay? By an infinitesimally small percent of that, or amount of that 10%. And you'd be like, how in the world can you do that? How can you divide something by infinity? Well, you can with advanced mathematics, namely limits. So this right here is the one formula I didn't tell you. A equals PE to the RT. This is what happens if you have continuous growth or continuous decay. In some of our problems and some of the exercises here, it'll say something is growing continuously, or use a continuous growth model. And that's the formula that we're going to use. P is still your initial amount. E is that natural number, Euler's number. R is your percentage, and T is the time period. So here we go. Somebody mentioned inflation. Y'all know what inflation is? It's like, what's inflation, Kevin?
Inflation is like when if you boost the value of everything else, so it kind of cancels out because that value going more.
Okay, that's kind of a good approximation. Sort of, I'd say that's a good first approximation. Part of the idea of inflation is that $5 today is not going to buy, as much as $5 bought, 10 or 15 or 20 years ago. Okay. As you say, like the price of everything kind of ends up getting inflated. One way you could think of it. All right. So 20, and you might be like, oh, I'm going to be a millionaire. Well, right now, a millionaire is awesome. Okay, it'd be great. Okay, but in 50 years, maybe like being a millionaire is not going to be so special because you can't buy as much stuff with $1 million in 50 years. If that makes sense. So you can't buy as much with $20, now that you could buy with $20 50 years ago. All right, so we're going to look at some of these problems, that way you kind of see what's going on. We're not going to do all of them, but we'll do enough of them. So this says the rate of inflation is 1.9% per year. The future price in dollars of a certain item can be modeled by the following exponential function, where t is the number of years from today. All right. So they're sort of applying that formula here. You can see the initial amount, and then this is embedded in here is the 1 plus 0.00, or the 0.019. So anyway, find the current price of the item and the price 10 years from today. Round your answer to the nearest dollar as necessary. So if we're talking about today, so the current price, that means when t equals 0, so after 0 years. We can do that, no problem. So p of 0 equals 1500 times 1.019 to 0. Anything with 0 is 1, so this is just going to be 1500. So it's what you can buy right now, $1,500, products, $1,500. How much would that same thing cost 10 years from now, assuming that the price is going to inflate 1.9% per year? So we put 1,500, 1.019 to the 10. This is a calculator drill here. What do we have, folks?
1,810.
Say it again?
1,810.
1,810.
0.6. I don't know if you need that.
Let's see. They say round to the nearest dollar. So if it's 0.6, they'll round up to $11. So 1811. So there you go. If you've got something, an awesome $1,500 computer, you can buy an okay computer for $1,500. You can buy a pretty good computer for $1,500. All right. if you want to buy an equally awesome computer, that's a bad example because computers go down. Okay. A car that might cost you $1,500, like a 5-year-old car. Once again, cars depreciate a whole lot. Anyway, something that you buy right now for $1,500, if you wanted to buy that same thing, sort of in the same condition, all right, in 10 years it's going to cost you $1,811 because the price gets inflated. All right, and you say, why does the price go up? Why does the price? Anybody know why did the price of things go up? There's several answers to this question. Emily, what's one reason?
The minimum wage goes up.
Oh, that's a great thing. Yeah, minimum wage goes up, ladies. So instead of, everybody having, what's minimum wage right now? $7.25. Okay, and so that's sort of like built into the cost. They bump it up to $10. Okay, well, guess what? If those companies are going to make money to pay their employees to buy all their stuff, then they're going to have to raise the prices, so the prices go up. That's one way. If minimum wage goes up. Fuel. If gas prices go up, then the price of shipping your product from the boat that it came over here on to your store, that's the price of gasoline is going up, so the price of diesel. So gas prices can cause inflation. Okay. Also, this is kind of getting a little technical, but also just the amount of money, like the amount of dollars that are out there. Okay. If the Federal Reserve decides to, they print a lot more money. If they say, you know what, we're kind of running low on money right now, let's just print a couple extra $1 trillion. Okay, so now there's a whole lot more cash flowing around. Well, it's just like anything. If there's a huge now supply, then the demand's going to go down. So that each one of those dollars is now going to be worth less. You can find examples of some of these countries in the last 100 years or whatever, where they've solved their problems of their debt is by printing more money. And they're like, oh, we owe you $1 million? Well, just print a printing press, here you go, here's your $1 million. That severely devalues the value of the currency. In fact, after World War II, my dad told me that he would watch documentaries on, like, East Germans or whatever, I don't know, I can't remember the exact details, where they'd be going to the bank with wheelbarrows of cash, and using the money, the paper money, for insulation in their houses, because it was worth more to use the money for insulation than it was to actually spend on anything, because the government just printed so much money. All right, so some interesting things there. Let's look at number 2. Radioactive substance, uranium-240, has a half-life of 14 hours. If you remember, we talked about that before. That means every 14 hours, half of it is going to dissipate in terms of energy, or into energy. The amount of a sample of uranium-240 remaining in grams after T hours is given by this exponential formula. So we've got 1200 times 1/2 T to the 14. Find the initial amount of the sample and the amount remaining after 30 hours. So how are we going to find the initial amount, class? Plug in 0. So A of 0 is 1200, 1/2, 0 over 14. Well, 0 divided by 14 is 0. Anything to the 0 is 1. So we just end up with the 1200. What about after 30 hours? How are we going to solve that one? So you plug in 30. Plug in 30. Okay, so you plug in 30. So you've got 1200, 1/2, 30 over 14. Anybody have a number there? Round to the nearest gram.
272.
A little louder.
272.
272? All right, there we go. So after 30 hours, we only have 272 grams left. Okay, let's skip on to something that looks a little more interesting. You like the next problem? Initial amount. When it says initial amount, what do you think that means?
0.
When what is 0? Time. Yeah. Initial amount, you need to, that means when t equals 0. They give you the formula right there.
Oh, no.
Oh, well, there's no t. H, which is hours. Okay, so when h equals 0. Amount after 8 hours means when h equals 8. And you can just plug that into the formula. Okay, let's keep going. Find something a little more pre-cal worthy. All right, here we go. Number 5. This is where they're no longer giving us the equations here. Suppose Miguel borrows $7,000 at an interest rate of 19% compounded each year. Wow, 19%.
That's a really bad loan.
Sure.
On the one above it, this is round to the nearest number. We need to round up, right? Because on people, you always round up, right?
It says whole number, so I would do regular rounding.
Regular rounding, because I know statistics, you always round up with people.
Right. Since they're specifying the whole number, I would say I'd round down. If it's like 0.2, yeah.
Okay.
And let me know if it doesn't work out for you.
Okay.
All right, good question. So number 5, we've got Miguel borrowing some money, 19% compounded per year. Follow the instructions, do not do any rounding. Okay, fine. Find the amount owed at the end of 1 year. Well, this isn't too bad. It's just going to be at 7,000 times, we could say 7,000 times the 19%, so 0.19. How much interest is he going to owe, folks? Say again? 1330. That's 1,330. Okay. Okay. That's how much he's gonna owe in interest. So we're gonna. This says how much he's gonna owe. Well, he's gonna owe that much in interest plus the original 7,000. So 7,000 plus that 1330. So $8,330. Find the amount owed at the end of 2 years. Okay. Isn't there an easier way of doing this?
The formula.
Yeah, let's use the formula. You want to use that formula? Yeah, let's use that formula. That's final amount is the principal times 1 plus the rate, 0.19. And then if it's after 2 years, we put 2. I could put principal 7,000. So I don't want to take this 8,330, multiply it by 0.19, and then add it. I don't want to mess with that. I just want to do this formula right here. Anybody have a number on that? Should be probably in the 9,000 region. 9,913.
So I think this is not too round.
Don't do it around. So what they have is 9912.70. For the record, we could have done that same formula for the first one, for that 8,330. That just would have been 7,000 times 1 plus 0.19 to the first. Okay, let's find the next problem that looks a little bit different than that. Okay, read 8 to me, Kevin.
A certain forest covers an area of 1,900 kilometers squared. Suppose that each year this area decreases by 7.75%. What will the area be after 14 years? Round your answer to the nearest square kilometer.
Okay, so this is good. We've got a decay amount. So formula is going to be just essentially the same. Instead of compounding, it's sort of decreasing. So the final amount is going to be the initial amount. That's your 1,900, and then the difference is we put 1 minus. 7.75% is 0.0775. It's compounding every year. That's nice that they wait to deforest, until December 31st, and for 14 years. Just all happens in one time. They said chop the whole section of force down. It's right then at the end. It's probably gradual, at least round your answer to the nearest square kilometer. So, what do y'all have? 614? All right. And we want to put, square kilometer. All right, so that's a little bit different. We've got to figure out how to utilize formulas. So, I don't know, y'all ought to be like getting antsy to start the homework yet. Y'all getting antsy yet? Looks really easy. I think y'all will be doing just fine on this. All right, let's look at somebody else. Find me another one that's slightly different. Ooh, what's different about 10?
It's quarterly.
Quarterly. Okay, I like that. Read that to us, Brooke.
Suppose that $2,000 is invested at a rate of 4.1% compounded quarterly, assuming no withdrawals are made. Find the total amount after 8 years.
Okay. So final amount is the principal. So it's $2,000. Is this going to be a 1 plus or 1 minus, class? Plus, because it's invested, it's growing. So this is 4.1% compounded quarterly. So I'm going to put that 0.041, and I'm going to divide that by 4. So it's around 1.025% each quarter. My exponent, now this is 8 years, so you might be like, okay, so I'm just going to put an 8 right here. But that's not how many times it's actually compounded. It's compounded 8 over the course of 8 years, but 4 times every year. So that's why we have to say times the 4. All right, number 10, somebody have a final answer? The nearest cent, I guess. 2771.75. Alex agrees. That is my answer key. Okay, so that's great. So we've got one that's compounded quarterly. Let's keep going, see if we can find anyone that's slightly different than that. Okay, what's different about 11? Ooh. That's a good one. So the car is purchased for $37,000. Each year it loses 25% of its value. After how many years will the car be worth $11,600 or less? Okay, that's kind of a good question.
Could we just plug it in and see the y equals? I mean, like plug in I don't know how the formula into the y equals and then look at
If you want to, yeah, then you could maybe kind of like, you want to table it or something like that, or trace it. Yep, absolutely, you could do that. And if what she's suggesting is just plug in the final amount equals 37,000 times 1. Is it going to be plus or minus? Excuse me, minus 0.25. Each year. Now here's the catch, we don't know how many years. So you can just put an X right there, and then you could graph it or table it and see when does it drop below 11,600. Great solution. I'm not gonna, if you want to do that, that's fine. I want to show you another way of doing this as well, and that is actually plug in the final amount of 11,600. Okay, so over here, right, 11,600, and then solve this exponential equation. Technically, we could say we want to figure out when is this amount less than or equal to 11,600. So the way that I've been solving these equations, I'm going to divide both sides by 3,700, and I'm just going to sorry, 37,000. I'm not even gonna bother doing approximations, I'm gonna leave it like that. Greater than or equal to 1 minus 0.25, that's 0.75 to the t. So what we have here is an exponential equation, alright? And remember, one of the ways we solve exponential equations is with logarithms. So let's turn this exponential equation into a logarithm equation. We could say log base 0.75 of 11,600 divided by 37,000 equals t. So you've got the log base feature on your calculator. So you put log base with the 0.75, and then I'm not going to bother with any decimal approximations. Just going to write 11,600 divided by 37,000. What do y'all get for t? What's the exact answer that you get? 4.03.
What's the smallest possible whole number is going to have to be 5 because at 4 it's still not going to be under 11,600.
That is correct. After 4 years, if the price is going down, but it hasn't hit that 11,600 yet.
No.
After 4.03, we're going to hit that 11,600. Okay, but so this says how many years will the car be worth that much or less? So smallest possible whole number, we're going to have to say 5 years. Stephanie, did you try it with the table? Did it work out? You're able to see it. So you probably saw it as like 37,000, then like 31,000, and like 25,000, or 26, something like that. You saw it going down, and you just finally did it. Either way you want to do that, that's fine. I just wanted to kind of tie this into logarithms since that's what we've been talking about. If you look here at number 13, LaShonda deposited $6,000 into an account with 2.1% annual interest rate. She needs to talk to that guy that borrowed at 17 or 18%, right? She's putting her money in the bank. She's only getting 2%. He's borrowing money from the bank, and how much was he paying? 19%. Yeah, you wonder how the bank makes money, right? All right, and that's not a bad. I mean, that's what they do. If you're gonna borrow money from them, then they're gonna charge you a whole lot more. If you're giving money to them for them to, to spread around and stuff like that, they're gonna give you a lower percentage rate. They're taking more risk because they're giving it to the individuals and stuff like that. And so they make money, but that's why that's their business model. So anyway, this is just semi-annually, so make sure you want to put that over 2. And this is going to be very similar to the one we just solved. Here we're looking for how long is it going to take to reach that 7,500. Okay, do y'all want to set this one up real quick? She deposited 6,000, so there's your initial amount. Is this going to be 1 plus or 1 minus? 1 plus because it's growing. So 1 plus 0.021, but it's compounded semi-annually. So I'm going to divide that by 2. The exponent here is going to be 2t. And we're going to figure how long will it take to grow to reach 7,500. Now, Stephanie, you might run into some problems with this one because if you try to table this and look and see how long it goes, because your x values are probably going up by ones. And this is asking to go by the nearest hundredth. Now there is a way you can change the table setup to go increment by hundreds, but then you're going to have to be hitting that up and down arrow quite a lot. The way that I would recommend that you solve this is similar to the way that we started to solve that other one, namely use logarithms. Alright, so first thing, I divide both sides by that 6,000. When I do, so we have 7,500 divided by 6,000 equals, what is this? I don't know if we can. 1.01. Okay, yeah, and that's totally exact, right? 2t. A couple nice things here, those zeros cancel out. You could reduce it even farther, 65 or 75 over 60, but whatever. And then we just want to convert this exponential equation into a logarithm equation. We could say log, what's the base class? Yeah, 1.0105 of 75 over 60 equals 2t. So you can take that into the calculator, and then whatever answer you get there, you're going to need to divide by 2. So t equals, let me know if anybody has a number there. Joe. Anybody have a final answer on that? Anybody agree or disagree with the 10.68? See some heads nodding. Alright, make sure you, it's good to practice through these. That way you can verify you get the right answer. Alright, let's keep going. 14 looks kind of similar. Look at that next page. What's another problem y'all would like to solve? 15 through 19. Pick a problem, any problem. What you got, Harley?
Let's just do 15.
Alright, read it to us then, please.
Suppose that the velocity v(t) in meters per second of the skydiver falling near the Earth's surface is given by the following exponential function, where the time t is the time after diving measured in seconds.
I'll read it. V of t equals 89 minus 89 e to the negative 0.16 t. Keep going.
How many seconds after diving will the skydiver's velocity be 67 meters per second? Round your answer to the nearest 10. And do not round any intermediate.
Computation. Okay. Alright, so they just want to find out how long is it going to take for the skydiver to reach 67 meters per second. So we've got a formula here for the velocity. So we could, if we want to, plug in any particular time into this formula, and it will tell us what the velocity is. Okay, that's a little bit too easy for us. The level that we're at is we say, all right, I want to know when is he going to be traveling 67 meters per second. So in other words, I want to know, find the t when v of t is equals 67. Hopefully you said meters per second. So in other words, when is 89 minus 89 e to the negative 0.16 t equal to 67? And we've just got a nice exponential equation here, no problem. And we're just going to end up solving for t. So let's subtract 89 from both sides. So Negative 89, e to the negative 0.16. Help me out, class. 67 minus 89. Negative 22. We will then divide both sides by 89, or by negative 89, and we get e to the negative 0.16 t equals a negative by a negative is a positive, and I'm just going to leave it as 22/89ths. And then just like we were doing before, convert this exponential equation into a logarithmic equation. So we'll say log base. It is natural log. Okay, well, if I said natural log base, that'd be kind of redundant. So, but yes, natural log of 22/89 equals the exponent, negative 0.16 t. So it's real basic here. Key in natural log 22/89, enter, divide by negative 0.16, and you end up with t is approximately, because we're going to round to the nearest 10th. Say it out loud. Here's somebody whispering. 8.7. So 8 seconds to be going 67 meters per second. Wow, you ever thought about that? 67 meters per second? So if 1 meter is a yard, we don't think of meters per second, so we just got to multiply it. Alright, think of it like yards, okay? So like 67 yards, like football. Well, we don't have football either. Okay. If you maybe watched football, you know, okay, or something like that, or, you know, maybe if you run track, you kind of know 100 meters, so we're 67 meters, we're kind of falling. So you're going that far a second. That's pretty fast. Alright. Scan through the rest of these. See, this one has a formula. 17 does not have a formula, so maybe we should deal with that one.
Is that, yeah. It's compounded continuous.
Yes. It says suppose that $1,100 is borrowed for 6 years at an interest rate of 5% per year, compounded continuously. This is what I kind of started off here. Find the amount owed, assuming no payments. By the way, I don't know of anybody that compounds continuously. That's just kind of ridiculous. All right. You might say, oh, I'm going to have unlimited money. No, it actually approaches a limit. Sorry. So we're going to use that formula. The final amount equals the principal times e to the RT. Compounded continuously, so we've got 6 years. So that's t equals 6, 5%, so the R is 0.05, and the initial amount, P is $1,100. So it's literally just plug that into the formula. 1,100 e to the 6 times 0.05, and rounded to the nearest cent. I get a 1,400. Wait for somebody else here.
1,484.84.
Okay. Kind of interesting. 84. Going there. Yep. 18, very similar. How much would be owed after 4 years? 19, he wants to buy a bond 7 years. How much should he pay for the bond now? Okay, that looks like a little bit of a different problem.
Are you finding the principal amount, aren't you?
Yeah, you're finding the principal amount. Okay, I'm gonna let you kind of figure that one out. Alright, so let's save that one for the homework. This one, number 20, how much should be invested now at an interest rate of 6.5% compounded continuously to have 2,000? Same kind of idea. Let's skip on down here. 21, biologist is a 391 gram sample of radioactive substance. Find the mass of the sample after 6 hours. If it decreases, according to a continuous exponential decay model, at a rate of 0.04% per hour. Okay, so here our time is hours rather than years. If it's an exponential decay, just to be very clear, that's going to be the final amount is PE to the negative RT. That's the only difference there. You're given the initial amount, you're given the rate, you're given the time. They just want you to find how much you've got at the end. And I think that's going to take care of all of that. Compound, how many years, and then there's the answers. Do y'all have the answers from back? I think.
No.
I didn't copy it for you. Okay. All right. I've got a deal for you. All right. Here's what I'd like to do. I feel like we've had a lot of quizzes in favor of spring break. I would like to just cancel tomorrow's quiz. How's that sound? Is that okay to you?
That's all.
What's the catch, right? There's a catch. All right, here's the catch. I need you to email me your parents' email or a good phone number for me to do a quick parent-teacher conference with them. All right? So give me an email that they'll reply to, or a phone number that I can get a hold of them. They are my biggest class, and I've got to contact every single one of your parents at some point. Okay?
Would
So
you like to email you then?
all I gotta do is email me. Email me something that they will respond to, whether it's a phone number or an email, and that'll be good. Send me that. And what we'll do is the homework that is officially due tonight, I will make officially due tomorrow night, and in class you can work on this homework. How's that sound? Make sure you get me that contact information. Otherwise, I'll make you take the quiz. Just kidding. Alright, so quiz is officially canceled and will never appear ever again. But just get this homework, 10F and 10G, taken care of by 11 o'clock tomorrow night. That's exponential growth and decay.